Math 2312, Section 1.2, Domain and Range. It was brought to my attention by a few students in class that I had assigned you one or two questions from the homework for 1.2 that I did not cover, either in class or through a supplemental video. So here's the supplemental video. The topic that I did not cover yet is called piecewise functions, and they're pretty easy to spot a mile away because you see something written in function notation like f of x equals or g of x equals, but immediately after the equal sign you see this tall brace capturing two or more functions. For example, f of x is equal to two functions, x minus 3 and negative 2x plus 1, but you can't use both of them at the same time because a function is only supposed to produce one output for a given input. Each part of a piecewise function has a condition attached to it, a condition that tells you when to select a function based on the input. In this case, for the function f of x, we have f of x equals 8x minus 3, but only if x is greater than or equal to 2. Meaning that if we put in a value that is 2 or greater, then we're going to do this function to it. But the other half of this function says f of x equals negative 2x plus 1 if x is less than 2. Meaning that if we put an input in that's less than 2, this is the function we're going to apply to it. Now, I wasn't around when they invented math or the notation, but if I were, I would have changed the way this looks a little bit. The problem with piecewise functions is that the condition you use to select your function is at the very end of it. If I had invented the notation, I would have started by saying the conditions on the x and put them to the left of the function followed by a colon. It's a little bit out of whack here. I'm going to put it back the way it was in a second. In fact, let me just erase this because I know what that part says. But if I had invented the notation, I would have not put the condition at the end of the function. I would have put the condition at the beginning. Meaning, it would have looked something like this. And again, this is my own personal preference. I would have written the functions f of x equals, if x is greater than or equal to 2, it equals x minus 3. If x is less than 2, it equals negative 2x plus 1. That way you can't physically read it left to right without looking at the condition that tells you which function to use. If you put it at the end like it's typically written, then you may forget to read that far and just say, I'm going to pick a function. I mean, it's not really that big a deal to look a little further to the right, but it's nice when you read things left to right to see them from left to right. Think of it as these are doors, like restroom doors at a restaurant. And before you go take care of your function, you have to choose the correct door to go through. Now, normally that door is chosen based on what's on the door, something indicating man or woman, and the gender that we'll say that you identify with or you're biologically assigned. We're not going to have that discussion right now. But you figure out which door to go through, and then you go through that door and do whatever is behind that door. The way function notation is written standardly for piecewise functions, the door that you have to choose isn't written until after you're already in the restroom, which kind of defeats the purpose of having the door in the first place. But anyway, when you do a piecewise function, you have to choose your function based on two pieces of information. What's your input and what are the conditions imposed on the input? Let's take a look at this one. Where we're being asked to evaluate f of 3, f of 1, f of 2, and our function is f of x equals x minus 3 if x is greater than or equal to 2, but it equals negative 2x plus 1 if x is less than 2. To evaluate a piecewise function, the first thing you have to do is pass judgment on the input as to which inequality it satisfies. Remember, the input without further information can be assumed to be an x value. In this case, x is equal to 3. And which of these two inequalities does 3 satisfy? The top one. 3 satisfies the inequality x is greater than or equal to 2. Sorry, these markers are kind of giving out on me. I don't think I have many more with me right here. Anyway, 3 satisfies the inequality x is greater than or equal to 2. And since it satisfies that inequality, that means we're going to choose the top function. We're gonna do 3 minus 3, which of course would give us 0. Same thing for all of them. You simply choose which function based on the input, in this case f of 1, and the inequality it satisfies. Since 1 satisfies the inequality x is less than 2, because last time I checked 1 is less than 2, then we're going to use the bottom function, negative 2x plus 1, to this input. So negative 2 times 1 plus 1, that equals negative 1. The only time you really have to be careful is when you put in what I call the boundary value, the value that separates the 2 inequalities, which in this case is 2. It's usually a matter of just looking for which one says or equal to. In this case, the top one does. 2 does satisfy x is greater than or equal to 2. So we would use the top function, which says take your input and subtract 3, and we get out negative 1. The same thing over here. The only difference over here is, well, I invite you to pause the video and try it. G of x equals x squared if x is greater than 0. And it equals 2x plus 2 if x is less than 0. Evaluate g of 2, g of negative 2, and g of 0. So go ahead and pause the video and see if you can evaluate those, or just look at it and think about it, because neither one is too terribly hard. And now we're going to do it. When we put in 2, you just have to look up here and say which inequality does 2 satisfy. It satisfies the top one. It satisfies the inequality x is greater than 0, which means I'm going to use the top function, which says give me an input and I'll square it. G of 2 is equal to 4. Well, what about negative 2? Negative 2 satisfies the bottom inequality, which is x is less than 0. And by the way, you don't have to write these inequalities beneath the inputs. I'm only writing them to demonstrate we're checking these inputs with these inequalities and finding the one that it satisfies. In this case, negative 2 satisfies the inequality x is less than 0, so we're going to use the function associated with that condition, 2x plus 2. So 2 times negative 1 plus 2, which I believe is negative 2. But what about 0? What does this function do with 0? It satisfies neither inequality. 0 is not greater than 0. 0 is not less than 0. So what does this function do to the number 0? The answer is nothing. You didn't tell it what to do when you gave it 0. This is undefined. Because this function does not know what to do when you put in the number 0. The reason I wanted to do that was to point out that when you have a piecewise function, sometimes you have not really domain issues, but a domain discussion, if you will. For example, this first function, f of x equals all this. What is its domain? Well, is there any number I can't put in? If I put in a number that's greater than or equal to 2, it goes on the top. Otherwise, it's less than 2 and it goes on the bottom. This domain is all real numbers, negative infinity to infinity. But what's the domain on this one? Can this function take in any value? Almost. There's only one value it can't take in. Based on the conditions imposed, it can't take in the value 0. Any other value it can. You have a number greater than 0, use the top function. You have a number less than 0, use the bottom function. But this function doesn't know what to do with 0, which means its domain excludes the number 0. Otherwise, it's in the domain. Any other number is in the domain. So negative infinity to 0, close that interval with the parentheses, union, open up the next interval, resuming after 0, going to infinity. So piecewise functions are actually pretty straightforward. You ask yourself which condition, which are listed at the end of the function, which condition does the input satisfy, and based on that decision, use that function. And it is possible for an input to not satisfy any condition, in which case the function is undefined because that value is excluded from its domain. In the next video, we're going to talk about how to graph both of these.